January till 2009. So I looked at her sort of publication list. She was a tour de force when she was here, publishing so many papers that we can only estimate. And after that, she got an NSERC postdoc fellowship to go to NOAA to work with Steve Brown and worked on different things: wintertime chemistry, nitrogen chemistry, chlorine chemistry. And then after that, she was in Memorial University for a few years, where she was a professor there. And then we're very fortunate that she has returned to Toronto, and now she's at York University. And she's the Guy Warwick Rogers Chair, which I assured is not an actual chair. And she's going to talk about aerosol brown carbon and maybe more.
Thanks, Arthur. So thanks everyone for coming this afternoon. I am going to be talking about some aerosol brown carbon, and after I submitted my abstract, I was making my talk for the AGU, and now it's making noise.
This is what I was telling you about, see? It always happens. It's the 10 after first.
Okay.
Okay.
So I was making my presentation for the AGU, and I got really excited about this, so I thought I would add in a little section about increased Arctic deposition of persistent compounds as a result of the Montreal Protocol. So in my group, technically I'm an analytical chemist, so we use and develop new analytical techniques, but really the goal is to understand processes in environmental chemistry. And my interests are many in environmental chemistry, indoor chemistry, air quality, and today I'll be talking about chemical drivers of climate, mainly the work of Rob DiLorenzo, who did a PhD in my group, and also a little bit about fate and transport of contaminants from a recent master's graduate, Heidi Pickard. Okay, so when I was a student at U of T, I was very ignorant about what was going on at York University, but it turns out that they have an atmospheric chemistry history that's older than I am. They've been doing atmospheric chemistry research there for a very long time. We have some great facilities up there, including an air quality research station, a rooftop lab. I inherited all kinds of great equipment from recent retirees, including a reaction chamber. And not once in my 9 years as a student at U of T did I go to York. And of course, the reason was it seemed like the end of nowhere to me. Very, very sad about this buzz. But now, as you probably know, we have this fancy new subway, and everyone is so happy. I mean, going up the stairs in York subway station it's just, everyone is giddy. They've been waiting so long for this. And I checked yesterday, and it turns out from this building to my lab, including walking, is 46 minutes. So we're very close now, and I hope that that means that we'll have a little bit more back and forth, and it won't just be me sitting up there by myself. So please come and visit. Okay, and now on to science. Okay, so aerosol light absorption is obviously a really important aspect of climate change. These aerosols can absorb light and influence climate. This absorption is typically dominated by black carbon, which is a wavelength independent absorption. We characterize this also as water insoluble. But there's also a wavelength dependent absorption that we can observe. And this is the water soluble component typically of the aerosol, and it's brown in color, and we call it brown carbon. So we have a fair amount of real evidence for brown carbon absorption from biomass burning organic aerosols in particular. This comes from the wavelength dependent residuals after we subtract the amounts of black carbon as well as mineral dust. So this is from optical measurements. And we can also observe them in offline by dissolving particles in water and observing the absorption in solution. Unfortunately, the uncertainty in source and composition of this brown carbon makes it really difficult to understand the potential climate impacts. There has been one really nice study out of Carnegie Mellon that looked at temperatures without brown carbon and including brown carbon, and the difference is about 0.5 watts per meter squared. And just as a reference, the radiative forcing of CO2 is 1.68 watts per meter squared, so that's fairly significant. And so this could be a really important contributor to radiative forcing, and it's essential that we understand it better. So what is it? That's really the question. The chemical structure is largely uncharacterized. It essentially is a natural organic matter, and that's extremely difficult to characterize. So there's been a number of laboratory studies that have tried to form brown carbon from things that you might find in the atmosphere, like ammonium and common aldehydes. And from that, you can mix those together and make brown stuff. That stuff absorbs. We've also seen particle extracts examined using various analytical techniques, but it's not that easy to get real biomass burning smoke samples because we have to know where fires are. So what do we know? It's commonly likened in the literature, brown carbon to humus. So this is a structure of humic acid that I pulled off of Wikipedia. And those of you who know a lot about natural organic matter will know that every picture of humic acid that you find looks different because there's no real consensus on what it looks like. So saying that brown carbon is like humic substances isn't actually really that useful. But it's somewhere to start. Okay, so the samples that we got were from a forest fire that happened in 2013 in the summer. So in the boreal forest of northern Quebec and Labrador, there was a big fire, and this smoke plume went over St. John's. Can't really tell where that is. It's kind of over here, which is where I was at the time. In St. John's, Newfoundland, on July 6th, the particle concentration reached 120 micrograms per meter cubed, which is huge. I mean, they thought it was fog, actually. This is what it looked like. People were out running, but no, get back inside. But so it was extremely bad event for St. John. So we took out our aerosol samplers, and what I'll talk about first is our PM2.5 samples that we collected over 24 hours. And what we wanted to do with these samples, which were aged in the real atmosphere from a real fire, is apply new analytical techniques and see if we can learn something new about this complex mixture that is brown carbon. Okay, so we took a step back here and said, well, how can we approach this in a new way and learn something valuable with these unique samples? So we know it's a complex mixture of organic compounds, so that means analysis is non-trivial. That's my Scott Mabry tribute. It's one of his favorite things. As a first approach to characterization, we decided to look at how natural organic matter, such as humic acids, have been analyzed and see if we could learn something from that. So many of the recent great analyses that we find in the literature looking at humic substances have been using ultra-high res mass spec, typically in electrospray ionization negative mode and sometimes in positive mode. So our first step to looking at this as a comparison to many of the studies in the literature was to use this ultra-high res mass spec in electrospray negative and positive mode. We extracted our particles by sonicating in water and methanol. We analyzed using an Orbitrap. We were able to use one over at the MOE. This Orbitrap is really nice. It has a resolving power about 140,000 at mass to charge of 400. So for those of you who haven't seen this type of mass spec data before, it's a mess. So our spectra were really, really complex, kind of a forest of stuff. And if we zoom in, you can see even more that at every mass to charge ratio, we have kind of a cluster of peaks, which if we zoom in even more, you can see at each nominal unit, we have about 12 separate peaks. So this is a huge mess of stuff. That's actually, it's fairly challenging to unpack. Oh dear. Okay, we've had a translational error here. Hopefully all of my graphs don't look like that. Okay, so this is electrospray negative data. These are oxygenated one formula. This is NO and SO. So most of our formulas here are up in the oxygenated region. So we had over 5,000 of them. Most of them were between mass to charge 100 and 1,000, and the intensity maximum was between 200 and 300. So this is generally consistent with past electrospray negative analyses of biomass burning, organic aerosol. We basically see a highly oxygenated mixture. Oh, it looks okay. So we can also use Van Crevelen diagrams to assist in characterizing the materials. So our formulas fell into all the zones, basically, the 8 different defined regions. But we saw a lot of density in the lignin region, here number 6, which is consistent with what we would expect as lignin as a primary macromolecule and the fuel material for this fire. But didn't actually really tell us that much. Okay, here's the positive, electrospray positive data, which is not that useful, except you can see there's a little bit more nitrogen, which is the main point here. We can also see some hydrocarbons, that's that purple here. So what we can see in electrospray positive is that there's different, we're seeing different molecules than we were seeing in electrospray negative, but it is consistent with previous studies. So the differences between these two ionization modes really highlight the importance of approaching using different ionization techniques to actually fully characterize the mixture. So we take a look at, we assume that this circle represents all of the organic molecules in our biomass burning organic aerosol. We then select some of them through our extraction technique. If we ionize them in electrospray negative, we're going to see some of them. If we ionize in electrospray positive, we'll see some different ones, some of the same ones, but we're likely not seeing the full mixture. And electrospray ionization selects for polar ionizable molecules, not necessarily for molecules that absorb, which is what we're interested in if we're considering the climate impacts of aerosol organic matter. So less polar compounds won't be observed, and if we're going to do a full molecular characterization, we're going to need to fill in the gaps. So for brown carbon, we don't want to look at what ionizes necessarily in electrospray. We want to know what absorbs. So that's something we actually know how to do very well. We can select the things that absorb by using UV-Vis absorption spectroscopy. But without separation, UV-Vis doesn't really tell us anything. Almost any organic mixture kind of looks like the same blob of stuff. So we need to separate this prior to detection. So the age-old technique of liquid chromatography coupled to UV-Vis detection is something that we could use to look at this. There are very few studies that have tried to do any kind of separation in looking at absorbing species for atmospheric particle extracts. One exception is this study from 2012 from Clays et al. This is a fresh biomass burning sample from the Amazon. And they saw nitrocatechol, the dominant absorber in these fresh biomass burning PM2.5 hueless extracts. So what we see here is absorption wavelength as a function of retention time and colored by intensity. So this big spike here they've identified as nitrocatechol, which was a major absorber. So we decided to try this to see if what we can compare to this Clays et al. Study. So we used reverse phase LCUV. We used a C18 stationary phase, and we made the most non-selective gradient method we could. So we weren't trying to do anything nice. We had 45-minute runtime. We started with a really weak mobile phase, and we moved really gradually to a strong mobile phase to try and get as much stuff as possible. And what we saw was just a mess. So our blank here is in green as a function of time. This is absorption at 300 nanometers. Our blank's in green, and our water extract from our particles is in orange. So first thing to note is that we were using a really dirty instrument because organic chemists use it to characterize their stuff, and no matter how much we cleaned it, we could not get rid of these artifacts. So that's fine, but what is really noticeable is this peak, if you can call it that, between 10 minutes and 25 minutes. So we called this the unresolved hump. So this eluded between over 15 minutes. And we don't see anything, we don't see any evidence really of individual compounds, but if we look back at this Clays et al. Chromatogram, we see they're also seeing kind of an unresolved hump. We don't see in our system any evidence of nitrocatechol, but these types of molecules actually have really short atmospheric lifetimes. So in our age system, we might not expect to see nitrocatechol at all. But what we don't know is there's all this absorbing material here. It's not nitrocatechol, so what is it? So the absorption pattern that we see, so we're seeing maximum absorption at 300 and we're seeing it drop off, that's suggestive of very large molecules. That's the type of absorption pattern we expect to see for really big stuff. So a more appropriate technique to examine large molecules is not reverse phase liquid chromatography, but rather size exclusion chromatography. So this method separates molecules exclusively based on size. It's commonly used for polymers, and it has been very rarely applied to atmospheric samples. So as we separate as a function of time, the first thing to elute will be small. This is backwards. Anyway, small will come out last, and big will come out first. Okay. So we used an aqueous size exclusion chromatography system. We selected a column that went from 250 to 75,000 Daltons, or molecular atomic mass units. We performed our separations isocratically, and we added a lot of salt, and that's to reduce the likelihood of any chemical interactions between the brown carbon and the column. So we want it to be exclusively based on size. We don't want any kind of chemistry to happen in this column. So Rob developed a really neat internal calibration technique using two different STC columns with different mass ranges to do a calibration, and he used that to estimate the molecular weights that we were seeing. And an important thing is that, if anything, this is going to be a lower limit of the sizes of the molecules. So we took our particle water and methanol extracts, and we analyzed them and compared them to humic acid standards to verify our method. So the first thing I'm going to show you is Suwannee River humic acid. And we call these sunset plots. So I'll take you through kind of what we're showing here. On the x-axis is the molecular weight that has been inferred from the retention time. On the left-hand y-axis is the wavelength, and that refers to the colored stuff at the back, which is colored by intensity. And on the right-hand y-axis is the extracted 300 nanometer absorption. That's just to guide your eye for the type of absorption we're seeing. Okay, so for Suwannee River humic acid, you see an average at 4,500 Daltons and up to about 20,000 Daltons. So this is consistent with what we know about Suwannee River humic acid from the literature. So that suggests to us that our method is reasonable. So now if we take a look at our brown carbon extracts, we're seeing something, again, we're seeing large molecules, but we're seeing distinct populations at about 2,700, 1,900, and 500 Daltons, and our masses go up to about 10,000 Daltons. But an important thing to note here is that most molecules were greater than 500 Daltons. So that's much larger than we expected to find. And so we took a look at our size exclusion chromatography, which is in green here, and our reverse phase chromatography, and we integrated, Rob did his best to integrate the 15-minute wide peak in the liquid chromatography, and we found the peak areas were similar, suggesting that that unresolved hump is really these large molecules. So the absorbing fraction of the age biomass burning particles is comprised mostly of these large molecules. So this still doesn't tell us about the molecular structure. So the next thing we tried was to take this method that we developed to separate the molecules and put it into a mass spec. And what I'm showing you here is the size exclusion chromatography. So in black is the absorption again, and now it's been overlaid with the total ion current of electrospray ionization in the negative mode. So what you can see right away is that the shapes are totally different. And if we extract the two, so we're basically seeing two peaks here. If we extract that peak and take a look at what the mass data looks like, we're seeing the masses between 100 to 400 mass to charge units, which is a lot smaller than the 1900 Daltons that we're seeing in size exclusion chromatography. And if we look at the second peak that we see in the TIC, we see basically the same mass spectrum. So that doesn't really make any sense. We're seeing a complete mismatch between our mass spectrum and the masses that we would expect to see based on size exclusion chromatography. So our initial thought was, oh, maybe we have multiply charged ions, but we were able to eliminate that based on properties of the mass spec. We also thought we could have some fragmentation. This is still possible, but what we really think is happening is that our selectivity, we have a selectivity bias. So our total organic biomass burning aerosol has a subfraction that's absorbing. That's the brown carbon. Our extraction technique should be capturing all of them, at least the brown carbon ones. And if we look at electrospray, we expect that what we're actually seeing is just a tiny subset of what's actually doing the absorbing. So what we think this tells us is that electrospray isn't really an appropriate technique to characterize the absorbing fraction. It tells us what organic species are there, but not which ones are important for climate and for absorption. So we know that non-polar molecules can't be ionized by electrospray ionization, but they can readily be ionized by other techniques. And one example is atmospheric pressure photoionization, or APPI. We chose APPI to test out because dopant-free APPI is selective for molecules that can be ionized by photons emitted from a krypton discharge lamp. And this includes non-polar molecules, and it includes it's more selective for molecules that might be absorbing based on just how it ionizes. So APPI, we tested using the exact same method as the ESI that I just described. So here is our TIC for APPI. And okay. And if we overlay the, you'll just have to imagine, if I overlay the absorption, it's actually quite a good match. Okay. And if we take a look at the three different regions that we identify in the TIC, we can see that they actually show a difference in size. They're still not exactly what we would expect based on the size exclusion chromatography, but we're doing a lot better than with electrospray. So we see a much better match. Unfortunately, getting ultra-high resolution instrumentation for APPI is actually very challenging. So if you guys know anyone who has one of these, I'd be really excited to talk to them. So that kind of stalled that for now, except to tell us that maybe we shouldn't be using electrospray to characterize this type of mixture. So we went back to our samples and said, well, we don't have ultra-high resolution APPI, so what else can we learn without using mass spec? And during the same biomass burning episode, we sampled size-segregated aerosols using nano Moody, which collects 12 size fractions between 10 nanometers and 10 microns. So the particle size distribution of brown carbon can be really important. It could tell us something about its source, and it could affect how we determine its importance. So we use the same method, and here I'm showing the normalized absorption as a function of particle diameter. And most of the absorption we're observing in the fine mode. So between 100 nanometers and 1 micron, that's where the dominant absorption is. And we see a local mode maximum in the ultrafine mode, but of course, we have to keep in mind that this is an aged sample, and so this may not represent what we see in fresh emissions. And we checked to see in every size bin, we took a look at the molecular size distribution. So it's the molecular size distribution of the aerosol size distribution. And we see that the molecular size varies consistently across all the aerosol sizes. So we were really surprised by this. We thought there might be some different mechanisms driving formation in different aerosol sizes. But we see the same thing in every single aerosol. The last thing we really wanted to check was how does the size distribution correspond to other things that we normally associate with biomass burning? So biomass burning is often identified by molecular markers, so levoglucosan or potassium. And if the tracers are externally mixed with respect to the brown carbon, this could influence our conclusions. So a first test was levoglucosan. So levoglucosan mass loading is shown in black here, and then behind is our brown carbon distribution, and you can see right away that that's totally different. And with potassium is shown in red, and then the brown carbon at the back, again, totally different distribution. And Alex Lee from John Abbott's group sampled this same plume, or a plume from the same fire coming through Toronto, and actually observed the same lack of, the potassium and organic molecules were not in the same aerosols. So levoglucosan and potassium did not have the same distribution as brown carbon, which suggests that predictions of brown carbon presence or absence using these markers may not be reliable. We know that ammonium and amines are present in are because at the same time that we were analyzing these samples, Trevor Vandenboer and his student Brian Place were developing a new ion chromatography method to look at amines. And so this is a fantastic new method, and they wanted some samples to try it on. And so they took our biomass burning samples, and what we found actually ended up being really much more interesting than we had anticipated. So the ammonium and amine loadings are a really good match with the brown carbon. And not only that, the mass loadings of amines exceeded those of ammonium. So this has never been seen before. Normally, amines are found at loadings about 1,000 times less than ammonium. So this is an unprecedented observation. No biomass burning work or any real amine observation has ever shown that the concentration of amines exceeds that of ammonium. So what we think is happening here is some sort of transport phenomenon. So our possible amine sources are really the ocean. So the plume passed over the ocean during the aging process. So the fires are shown here by these red dots. And here's our sampling location over here in St. John's. And this is chlorophyll. All this color along the coast is chlorophyll, indicative of biological activity measured by satellite, I want to say. One of a satellite measurement of chlorophyll. Okay. And we know that diethyl and dimethyl amines are emitted from the ocean. So we think that there could be some uptake to brown carbon containing aerosols. That could happen reactively. So we know that amines and ammonia can react with carbonyls to form amines. And these amines can be absorbing. Unfortunately, in the way we do our analysis, if we form these amines, they would be hydrolyzed during our sample extraction. So we wouldn't see them as amines, we would see them as the original amines or ammonia. We could also be seeing the formation of stable salts. So we know that our organic matter, the brown carbon, is rich in oxygen, which could include acidic functions, and those could form stable salts with amines or ammonia. When we took a look at these same samples, we saw a major cationic excess. So we counted up all the positive charges and all the negative charges, and we had way more positive charges than negative charges. And that coincided with the increase in brown carbon. So what this suggests is that we aren't measuring a lot of the negative charges, which could be coming from the brown carbon itself. And that could be because we have this type of thing happening, or it could be because we have stable salts. So it's really consistent with both. But it suggests we have this unmeasured chunk of negative charge. So all data I've shown you so far have been from a single sample. And so we can't really extrapolate that. We have n=1 samples. And so we had a few questions we wanted to address, and we need more samples to do that. So is all brown carbon of large molecular weight origin? Is it just brown carbon found in biomass burning samples? If so, is the molecular weight distribution the same? And how do background air samples compare to biomass burning samples? We want to apply our new techniques to look at different samples and see how brown carbon varies. So my student Rob is very active on social media. And in July of 2015, former U of T alumni Jeff Geddes, now professor at Boston University, posted this satellite photo showing wildfire smoke in British Columbia. And Trevor liked it. So Rob posted, somebody please take aerosol samples and send them to me. John, this is where you show them. So we had some chemists and former chemists discussing where might Rob find some samples. Eventually, Jen Murphy suggested that Rob get in touch with Alan Bertram at UBC, and a couple months later, these aerosol samples showed up in the mail in Newfoundland. So Rob, from then on, wouldn't let me get him in trouble for being on Facebook. So we were able to get some more samples through a more traditional route. Rebecca Waschenfelder from NOAA participated in the Southern Oxidant and Aerosol Study, or SOAS, in Brent, Alabama in summer of 2013. And the purpose of this study was to look at SOA formation from biogenic precursors. So basically there was no biomass burning happening here. This is at ground air. So she collected filter samples for us in line after her spectroscopic measurement of brown carbon, which she did using a broadband cavity-enhanced spectrometer, and she collected daily samples. So we ended up with quite a few samples to look at. And this gave us some confidence. So we had 3 different types of samples. We had a St. John sample that was 48 hours aged. We had samples from Vancouver that were 10 to 24 hours aged. And we had this background air from Alabama, which we estimated was 2 to 5 days aged, but didn't have any explicit biomass burning influence. What we noticed when we took a look at these using size exclusion chromatography is, again, the same shape. So we're seeing the influence of large molecules. We see that it's consistent across all the days of the campaign, and that large species are consistently about 3 times the importance of small molecules. So we can put this all together now, and I'm showing you now the sunset plots from all 3 sites. So this is from British Columbia, this is from Newfoundland, and this is from the SOAS campaign. So we're increasing the age of the samples, and we see that the absorption profile is pretty consistent. So the peaks occur at the same molecular weights. We see an apparent decrease in absolute absorption intensity, but we can't actually calculate the mass absorption coefficients here because it's too difficult to know the total mass of the particles themselves. But what we can see is that there's a decreasing proportion of small molecule contribution to absorption as the aerosols age. So at first we have a fairly significant contribution from small molecules that really decreases as in relative importance as we age the aerosols. And we took this data that Robin collected, and we compared it to some really nice aircraft work from Rodney Weber's group at Georgia Tech. So they have been able to follow a fire and look at the brown carbon in that fire using an offline instrument. And they showed rapid decline of brown carbon absorption during plume transport. So really quickly, the brown carbon was dropping off. So we put our samples on here for context, and we aged them using back trajectories, so that's why there's so much uncertainty here. But we see that it's quite consistent. So all of our samples fall into this aged, sort of low absorption category. So we're still really seeing no change in overall absorption in these samples that are greater than 10 hours old. What we do see is an increased contribution of large molecular weight species with age. So if we take the ratio, the contribution of large molecules to small molecules, see an increase with transport time. So what this tells us is that the large molecules are either more persistent or they're forming through time. And it underscores the importance of understanding these large molecules to constrain climate impacts of brown carbon. So Rob, the last thing he did was to take this data and see if he could constrain the structure at all. So he took the molecular weights and put them into Neil Donohue's chemical partitioning space using the volatility basis set. And what we see is what we might expect, that they fall into the mostly into the extremely low volatility compound region and beyond. Okay, so to summarize this bit, we can say with some confidence that aged brown carbon is dominated by large molecules. It appears to be conserved among samples of different origin. And from a single age biomass burning sample, we determined brown carbon is enriched in submicron particles, externally mixed with respect to biomass burning markers, and we need to do more to characterize what the actual molecules are. And we're working on that right now. So we have some samples that Rebecca Waschenfelder from NOAA collected at the NOAA Fire Lab as part of the FireX study. And they burned lots of different things, and also artificially aged smoke that came from these fires. And we have particle samples that we will be analyzing using these same techniques to try and understand the composition. All right, in the last few minutes, I'm going to quickly take you through a really cool story that Heidi Pickard worked on for her master's, looking at the impacts of policy on Arctic deposition of contaminants. And this is a collaboration with Amila De Silva from Environment and Climate Change Canada, and Ali Crisatiello, who is a glaciologist at the University of Alberta. Okay, so perfluorocarboxylic acids are the persistent compounds that we're looking at They're ubiquitous in the environment, including the high Arctic, which is far from known sources. And they range in size, detected in the environment from very short, this is the C2 or trifluoroacetic acid, to C18 and possibly longer. They have potential ecosystem and health impacts, so we know that they bioaccumulate, they can act as endocrine disruptors, and many more things. So some perfluorocarboxylic acids are produced directly for use in industry, so the non-stick industry is a big one. But they can also be formed in the environment through atmospheric oxidation of precursor compounds. So this is actually fairly well understood chemistry from extensive small chamber work. Unfortunately, what we don't know is how prevalent this really is in the environment. So long-term trends of perfluorocarboxylic acids in the environment aren't really, they don't really exist. So we know that the C2PFCA or TFA can be produced in large yields, so greater than 10% from CFC replacements. Similarly, it can be formed in large yields from anesthetics and in minor yields from the fluoropolymer industry. The C3 PFCA or perfluoropropionic acid can be formed from CFC replacements and fluoropolymer industry. So the fluoropolymer industry is producing these in minor yields, so that's less than 10%. And C4 can be formed in minor yields from both CFC replacements and the fluoropolymer industry. And longer chain PFCAs are formed in minor yields from the fluoropolymer industry. So I'm going to refer to these ones as short chain PFCAs and the other ones as long chain, which I'm not going to really talk about today. So we have a lot of information about production trends of the potential precursor compounds. We know that in the 60s, halothane anesthetics started to be used, and in the mid-90s, another anesthetic. Both of these can form TFA. In the 1960s, that's when large-scale use of CFCs began, and it took us about a decade to realize that these were destroying the stratospheric ozone layer, and more than a decade to ban them. So the Montreal Protocol was enacted in 1987, and that is when replacement compounds for CFCs, hydrochlorofluorocarbons and hydrofluorocarbons started in large yields. Then we realized HCFCs were actually bad for the environment and stopped that, and now we've realized that HFCs are also bad for the environment, and we're starting to get rid of those. So in 2020, HCFCs should be totally gone. And around 1960, we had a lot of really great chemistry going on in the 1960s. That's when fluoropolymer PFCA precursors also started being used. So the idea for this study is that we can actually use the high Arctic ice caps as a bit of a time capsule to understand the record of atmospheric pollution. So these Arctic ice caps receive their contamination solely from the atmosphere. So they're typically fairly high elevation. The one we're looking at is about 2 kilometers above sea level. So they preserve this temporal record of deposition. And what I'm going to show you today is that we can use this temporal record to understand deposition of these short chain PFCAs and use that to elucidate sources of these compounds. So in 2015, this is Ali collecting our ice core from the Devon ice cap, which is all the way up here. It was a 15-meter ice core, and she dated it to go back to 1977. We sectioned it according to year, did some extractions, and analyzed using liquid chromatography tandem mass spectrometry. We also did some ion analysis, but I'm not going to talk about that today. Oh no, this is terrible. Okay. Should have obviously checked this. Max. So, yeah, okay. Blue is TFA, and then it actually doesn't really matter. The trends will be the same. Okay, so these are the 3 different short chain PFCAs. Pre-1990, we're not seeing any real change with time. And for reference, I'm putting on a long chain PFCA, and that follows the exact same trend. So if we go post-1990, the long chain one, we don't see any real trend. But if we put the short chains on here, they actually go way off scale. So we have to back it out. And when we back it out, we can see that around 1990, which you can't really tell here, we're seeing a major, major increase of these 3 short chain acids. Great, okay. So Trifluoroacetic acid, the precursors to these compounds are well measured, and the emissions are really well estimated because of the impacts on stratospheric ozone and climate change. So these are the emissions of known precursors. And we put on the TFA itself, you can see that we're seeing an increase starting around the same time that these emissions are increasing. And if we actually correlate, the mixing ratios and deposition show a strong and significant correlation. And same thing with the C3. So we have two precursors. This is the sum here. And if I put on the actual deposition, which looks like this, you'll notice it kind of looks like this. So we see a really good match of the emissions and precursors, and we see a moderate and significant correlation. So the C4 is a little bit more tricky because it's a minor, because we don't really have any information about the emissions or mixing ratios of potential sources. That means we have to be a little bit more creative. Oh, this one worked. Okay. So we can use some trends that we know from from the fluoropolymer products. We know that when those degrade, we will see a 1-to-1 ratio of the even to odd acids. So C10, C11, C8, C9, C6, C7, all these fall around the 1-to-1 line. But if we look at the one at PFBA, C4, C5, it's totally different. So what this tells us is that fluoropolymer degradation probably cannot explain the deposition onto the ice cap. There has to be something else happening, and that's likely contribution from the CFC replacements. So this is important, really important actually, considering the proposed new regulations. So because these CFC replacements impact climate, they're being regulated by the Montreal Protocol through the Kigali Amendment. So CFC 12 was replaced with an HCFC and also with an HFC. So HFC 134A is what you find in your car air conditioner. And the major proposed replacement class are these hydrofluoroolefins, HFOs. So HFC 134A is already starting to be replaced by HFO 1234YF. And this compound produces TFA in about a 20% yield, and this one produces TFA in 100% yield. So we're expecting that emission or deposition of TFA is going to really dramatically increase. But because of the chemical properties of HFOs compared to HFCs, the spatial distribution of this is expected to be very, very different. So the lifetime of this is short on the order of weeks. So these will not be well mixed in the atmosphere. And we expect that we'll see regional deposition. And that could have some really important consequences for ecosystems. Okay, to conclude, the deposition of these short chain PFCAs reflect the changes in emissions and mixing ratios of the precursor compounds, which are predominantly CFC replacements that are regulated by the Montreal Protocol. Increased regulation of these compounds through the Montreal Protocol is likely to influence deposition to the high Arctic, but we don't really know how that will, what the impact will be. Unfortunately, we don't know a lot about the impacts of, the real impacts of short chain PFCAs on the environment. But what we do know is that these compounds are very, very persistent. They have no known natural degradation pathways. So although the Montreal Protocol has been extremely successful in mitigating stratospheric ozone depletion and also climate change, with the regulations that we have in place now, we are committing the environment to long-term contamination with these contaminants, and then we don't really know what the impacts will be. Okay, and with that, I would like to acknowledge the following people, funding agencies, my group, and thank you for your attention.